Good evening to you all once again. I welcome you all for another beautiful presentation on electronic devices and circuits. We are seeing the various classifications of materials based on their energy gap diagrams, right? So far, we have seen about the insulators and then the conductors, as well as how their energy gap will increase or decrease, and what are the values of their energy gaps, right? In previous presentation also we have seen what is the relation between the applied electric field and then the drift velocity of electron, right? And we have seen the relation that Vd, or otherwise drift velocity, is equal to mu into E, means mobility into electric field. So thereby we can say that the drift velocity of electron is directly proportional to the applied electric field, right? In today's presentation, I would like to explain you one more important aspect or concept of the energy gap, basically, or energy band. What is the relation between the energy gap and then the temperature? Normally the energy gap will depends on the temperature. It is the function of temperature. How the energy gap will varies with the temperature, that we are going to see in today's presentation. Let us go into the subject and we will enjoy today's presentation. We are going to see electronic devices, and this is our lecture number 3 with respect to our electronic devices subject is concerned. And in this presentation, I would like to give you some important points which we have already discussed in previous presentation. This is based on the semiconductors. Based on semiconductors. So semiconductors are nothing but these are the materials which will exhibit the properties between insulators and then to the conductors. This we have seen in our earlier presentation, right? Semiconductors are the materials which will exhibit the properties in between insulators and then conductors. Those materials are called as semiconductors, right? And the best examples for semiconductors are germanium and then silicon. This is also we have seen germanium and then silicon, right? And if you consider the atomic number of germanium is 32 actually, whereas for silicon it is 14. What is this? Atomic number. Atomic number is 32 for germanium, as well as for silicon the atomic number is 14, right? And if you see the electronic configuration for both these silicon and then germanium, we have seen that both these have equal valence electrons, means this also will have valence electrons as 4, as well as your silicon will also have the valence electrons are 4. Both are having same amount of free electrons, are also called as valence electrons. That is why, because of this reason, the silicon and germanium are called tetravalent atoms. For this reason, these two are called as tetravalent atoms. And if you consider again, if you compare these two, silicon and germanium, the most and widely popular, available material is silicon actually. Silicon is very abundantly available in the earth basically. That's why most of the time we will use the silicon rather than germanium. The availability of silicon is very good. Abundantly it will be available in the earth actually. That's why in the manufacturing of any electronic component or electronic devices, the silicon is more preferable than germanium. Clear? So this is the basic just information about these two. Now if you see the band gap or energy gap diagram or the energy band diagram of the semiconductor, as I have already explained in the previous presentations, for your kind quick reference, I will explain you one more time this. Consider these are the two bands as we have discussed in our previous presentations. The bottom one is called as your valence band actually, and the upper one is called as your conduction band basically, and the gap which is there in between these two is called as Eg. This is what energy gap or otherwise energy band, whatever it is, right? So this is the conduction band, this is the valence band, and in between these two there is a small amount of gap that is called E suffix G, is nothing but energy gap or energy band, right? So for this is for semiconductors actually. This is the energy band diagram for semiconductors. For semiconductors, right? For semiconductors, the value of Eg is about 1 electron volt. Remember, very, very important bit. Okay, the Eg is about 1 electron volt basically, and which is very, very small. So the gap is very small, which is very small if you compare with your insulator. Whereas in insulator, the energy gap is about, in insulator, the energy gap is about 6 electron volt at least, and even the insulators may have more than this also, depending on the type of the material. This is the example for diamond basically. This is the energy gap for diamond, which is an example for the insulator, right? So the energy gap is more in insulators, right? So this is the value of energy gap for diamond actually. Coming to the semiconductor, it is the energy gap is about 1 electron volt, right? And remember that one important point here, what I want to convey you is that the energy gap is function of temperature. The energy gap is depends on temperature basically, right? The energy gap depends on the temperature, capital T, and most of the time this energy gap is measured in terms of electron volt. Remember, EV, small e, capital V. So Eg is measured in electron volts, whereas your temperature is measured either in degree centigrade, either in the temperature can be measured either in degree centigrade or otherwise degree Kelvin. Degree Kelvin, or in short you can write simply K, either degree centigrade as it is, or degree Kelvin is nothing but degree K, degree centigrade, degree Kelvin. So, and most of the time we will use degree Kelvin only. Most of the times, wherever the temperature is required to be mentioned, as far as our subject is concerned, consider degree Kelvin will be widely used. Degree Kelvin will be considered, right? So here, clear? So now I am going to explain you what is the relation between energy gap and then the temperature. What is the relation between these two? And before going to explain the relation between energy gap and then temperature, I would like to give one important note actually. Normally the different types of temperature come across while studying this subject. We will consider room temperature most of the time. All are you aware of this? Room temperature normally. Room temperature, right? So room temperature or simply T in degree centigrade. If you in degree centigrade, if you write the room temperature in degree centigrade, what is the value? It is 27 degree centigrade. Room temperature in degree centigrade is nothing but the value is 27 degree centigrade. Whereas the same room temperature in terms of degree Kelvin. So what is the value of room temperature in degree Kelvin? It is nothing but your 27 should be added with 273, thereby you will get it is 300. Then this 300 degree Kelvin is called as room temperature, right? The 27 degree centigrade will be, it is 27 degree centigrade value plus 273. If you add these two, then you will get 300 degree Kelvin. So this is the room temperature now in degree Kelvin. Therefore, wherever degree centigrade is given, then consider 27 degree centigrades in terms of degree centigrades, whereas in degree Kelvin, if you mention the room temperature, the value is 300 degree Kelvin. Remember that these two are. Therefore, right, this is the room temperature in degree Kelvin. So room temperature in degree Kelvin is 300 degree Kelvin. Remember that, right? And now the relation, what is the relation between, because the best example for semiconductors are silicon and germanium. Just now we have seen. Therefore, individually for both silicon as well as germanium, you will have their relevant, relation between energy gap and then temperature. Now I will write that expression for silicon. For silicon, the energy gap, the energy gap in terms of temperature, temp, I can write like this, can be given as this is Eg is equal to 1.21 minus, it is 3.6 into 10 power minus 4 times T. This is electron volt. This is the very, very important relation that everybody need to remember. Right? This is into T. So this is for silicon. Easy, this is for silicon. Right? So the energy gap for silicon, the relation between energy gap and then temperature, where T is the temperature in degree Kelvin. This is in degree Kelvin. Remember that. This is temperature in degree Kelvin. Right? Therefore, Eg, energy gap is equal to, Eg nothing but energy gap. Eg is equal to 1.21 minus 3.6 into 10 power minus 4 into T, where T is the temperature in degree Kelvin. Right? So this is the for silicon actually. Now here two important points I would like to explain you that. Say for example at T is equal to 0 degree Kelvin. What is? At T is equal to 0 degree Kelvin. 0 degree Kelvin. If I apply 0, then what will be the Eg value? If you apply 0 here, in place of T, you substitute simply 0, then 0 into everything becomes 0, then what is your Eg? Your Eg becomes, it is simply 1.21 electron volt. Therefore, at T equal to 0 degree Kelvin, your energy gap is 1.21 electron volt for silicon. And similarly at capital T is equal to 300 degree Kelvin. At temperature T is equal to 300. What is 300 degree Kelvin actually? It is the room temperature. This temperature is nothing but room temperature. Now substitute in place of T, substitute 300 here. If you put 300 here, 300 multiplied by 3.6 into 10 power minus 4 and everything, if you subtract that value from 1.21, you will get no Eg is nothing but 1.1 electron volt. You can calculate with your calculator that value, you will get this value. Eg is equal to 1.1 electron volt, right? So now clear. So at T equal to 300 degree Kelvin, nothing but it is the room temperature. At room temperature, the energy gap value is 1.1 electron volt. Now you can observe one important observation here. My temperature is increasing from 0 to 300 degree Kelvin. So it is 0 degree Kelvin and then 10 and so on and so forth up to it is 300, means I have increased the temperature. So here the temperature is increasing. What is happening to the energy gap? Energy gap initially it is 1.21 electron volt. As my temperature go on increasing, what happened to the Eg? It is decreasing. It is initially 1.21 electron volt. Now it has become 1.1 only. Means the energy gap is decreased. Clear? So means that what you can say, as the temperature increases, the energy gap will decreases. That is very, very important point actually. Right? So as the temperature increases, as temperature T increases, means you can use this symbol. As temperature T increases, then correspondingly your Eg, energy gap, what will happen? Decreases. Show the down arrow mark. This is one important relation actually. If you show the arrow mark in upward direction, that indicates increasing value, whereas if you show the arrow mark, down arrow mark, then it shows the decreasing value. So as your temperature go on increases, your energy gap will decreases. This is one important relation, okay? And these two values are very, very important in examinations, or especially in GATE examination, even in UPSC IAS examination. This question will be expected. At 0 degree Kelvin, what is the energy gap for silicon? At room temperature, or they will give you at 300 degree Kelvin, what is the energy gap of silicon? You must remember, do not confuse, do not confuse. Therefore, please you practice and remember that. So this is regarding to our silicon. Now the similar equation is there for germanium also. So now I will write for you for germanium. So for germanium, note down. For germanium, what is the relation? There is a similar relation, means Eg is equal to 0.785 minus, it is 2.23. It is 2.23 times 10 power minus 4 multiplied by T into T. Actually, this is the very, very important relation. This is the equation. This equation gives the relation between energy gap and then the temperature. This relation gives the details about the energy gap and then the temperature for germanium. Actually, this is the energy gap, this is the temperature, right? So this is the factor actually. You know what is this actually? Minus 2.23 into 10 power minus 4. What is this? Means the energy gap will decrease. The energy gap is decreasing, no? As you increase the temperature, your energy gap will decreases. Means that this factor, whatever is there, minus 2.23 10 power minus 4, indicates that this is the rate of decreasing per electron volt per degree Kelvin. This is the rate of decreasing. This factor indicates the rate of decreasing of the energy gap per degree Kelvin. Per 1 degree Kelvin, it decreases this much actually. That is the meaning of it. And similarly for silicon also, where we have seen it is 3.6 into 10 power minus 4, minus 3.6 into 10 power minus 4, means that is the rate of decreasing in case of silicon, right? And similarly, now you apply at T is equal to 0 degree Kelvin. At T equal to 0 degree Kelvin, what is the energy gap value? Energy gap value for germanium, this is for germanium we are calculating. At T equal to 0 degree Kelvin means simply you substitute wherever T is there, you put 0. Therefore, if you apply 0, everything becomes 0 and finally you will have 0.785 electron volt. That's it. That's it. This is the energy gap for germanium at 0 degree Kelvin, right? And similarly, what will be the value of Eg at T is equal to room temperature? What is room temperature? It is 300 degree Kelvin. So for this, what we need to do? You simply substitute in place of T 300. You just apply the value of 300 there. If you apply 300, if you multiply and you can simplify this with your calculator, you will get Eg is equal to, it is 0.72. That's it. That's it. This is the energy gap. So in the same way, what we observed in silicon, the same principle will be right here also. Means as the temperature is increasing from 0 degree to 300 degree Kelvin, your energy gap is also 0.785 to 0.72. It is decreased. So here your temperature is increased, whereas your energy gap is decreased. Therefore, these two values are so very, very important values. Very, very important values. Therefore, you please remember these values, and for 1 mark questions, normally these bits are very much, expected in your GATE examination as well as UPSC examination, right? I think I will finish off this presentation here, and we will see some more important questions and observations and topics in our subsequent presentations. I hope you understood well, and thank you for watching this video, right? Have a nice day.